Okay, hello, good afternoon. Welcome to this AUTOPILOT webinar. Today we will be presenting one of the automated driving pilots within the Brainport of the AUTOPILOT project. It concerns automated valet parking. In this presentation we have several presenters of parties involved in automated valet parking. It concerns Vicomtech, DLR and TAS. So this is the agenda. So I just made the introduction of the webinar. Then I will present a very brief overview of AUTOPILOT and the Brainport pilot site and some of the services that we have. We have seen that most of the attendees are familiar with the AUTOPILOT project. Then a presentation, a few slides will be presented by TAS on the IoT configuration and the functions. This is done by Amy Matthews. Vicomtech then will follow, will take over with the video surveillance application, and then DLR will present the drone application. And then I will close off with the next steps towards the pilots. I also show some results for automated driving. So what about the AUTOPILOT project and the Brainport? Well, the idea of the AUTOPILOT project is to have large-scale pilot combining automated driving and Internet of Things. And this is done by involving or executing automated driving use cases at different pilot sites, 5 pilot sites within Europe and 1 in Korea. And you can see we started last January, and we're just about halfway in the project duration. We have 44 partners involved, also several associated parties. So what is the challenge of AUTOPILOT that we are addressing? Well, we have to demonstrate the added value of Internet of Things for automated driving. And what we have, what we could say, there's a lot of information on the internet. And we want to use it for safety critical applications. And the question is, how can you do that? Well, and the solution is Internet of Things. With Internet of Things, we can get information which is beyond the reach of sensors. So, like we could consider the planned route on the navigation system. You cannot assess that from sensing. We also can put the data that we receive in context, so indicating the level of trustworthiness, because we can only use the data if we are really feel secure that we can use it, convinced that we can use it. And for that, we need to indicate some trustworthiness indicators. And finally, of course, Internet of Things is a great opportunity to connect anything as a source of information. On the other end, we have automated driving. There are 3 levels we can talk about. Is the strategic level, technical level, and operational level, related to travel planning, decision making, steer and speed control. And where we see the application of Internet of Things is mainly within the decision making process of automated driving. So the steering and the speed will not directly act on the information of Internet of Things, but the decision making, like which speed to choose or which lane to choose, that kind of application. So within the Brainport, we have 5 different use cases. The use case of car sharing considers the whole region of Eindhoven and Helmond. And then we have a use case on platooning, which is executed on the test road between here on the 870 test site between Helmond and Eindhoven. We have the highway pilot application, which also will focus on that road. We have automated valet parking and relocation. And relocation means to have unmanned cars driving to locations where people want to have cars available. So, as said, we focus in this webinar on automated valet parking. And yeah, what does IoT bring for automated valet parking, or what is automated valet parking? It means that you can leave your car and the car autonomously finds its way to a parking spot, and it will return to you on command. Of course, it has several benefits. It's a comfort service. We can have more efficient use of the space in parking lots. There will be less damage to cars. You can optimize the logistics on parking areas, and we can have a more efficient use for of EV charging spots, etc. So this is the test location we are considering. This is also the location where I am now. It's the automotive campus in Helmond, and we have different parties. So we are here in this office building. Our main activity on automated valet parking is the vehicle control and the Internet of Things. We have the control room of TAS. They connect to the monitoring system and provide IoT services. Then we have the facilities of the parking itself and fixed cameras. They are provided by the city of Helmond. There's a camera and drone application provided by DLR. DLR is actually the coordinator of the whole use case of automated valet parking. They're also involved in vehicle control and providing the IoT network services. And then we have many camera applications that requires image processing, and that is done by vContact. And finally, of course, we need vehicles to drive around, and the vehicles will be provided by Nefs, as the former Saab factory in Sweden. So what you can see here is the situation at the campus. So we have a drop-off zone in front of the building. And then there are different routes to the parking, and the cameras will observe the roads. Many times are trucks loading and unloading for the canteen. So depending on where other traffic is around, we plan the route to come to the parking area, and of course on the parking itself you have to find an empty parking spot. So this is where we're looking at for automated valet parking. So we can continue on the IoT configuration and functions. This will be presented by Amy Matthews, and I will now make Amy the presenter. So Amy, please continue.
Hello, my name is Amy Matthews. I'm working at TAS International. So in the next few slides, I'm going to explain how IoT is playing a central role in this use case. So if you look at this high-level architecture diagram, you can see that literally IoT is in the center, and we can see that there is an IoT platform. So what does this mean? What is an IoT platform? In simple words, we can say that it's a platform that allows IoT devices to communicate with each other using the internet protocols. So if you have not heard of any of the IoT platform, you can name any of the top 10 or 20 technical companies and you have an IoT platform. For example, we have Amazon. The most popular ones are the Amazon Web Service or Google Cloud Platform, Cisco IoT Cloud, or Oracle Integrated Cloud, Microsoft Azure. So quite a lot of IoT platforms are available in the market. And in the AUTOPILOT project, we are also fortunate to have two big players. One is IBM, and IBM is having the IBM Watson IoT platform, and also like Huawei is there. Huawei comes with their Ocean Connect IoT platform. And also another provider is a startup called Sensinov. They are providing a 1M2M IoT platform. So we have quite a lot of IoT platforms in the project, and especially in the automated valet parking, we are using two of these. One is the IBM Watson IoT platform, and the second one is the 1M2M IoT platform. So what is an IoT platform? So what are the functions? So how do you select the IoT platform? So this depends upon the use case you have. For example, what type of applications you are looking at. Is the platform able to support or handle quite a lot of high stream data coming from multiple sources? So how is the data, where is the data stored? Is it highly secure? Is it stored in the premise or in a public cloud? Quite a lot of things decide on choosing up the IoT platform. And in the AVP use case, we have DLR has chosen the IBM Watson as their IoT platform. And for the DLR has their own vehicles, and also the vehicles are provided by TAS TNO. So we have chosen the 1M2M as IoT platform. So now we have these two IoT platforms that needs to also work together in the use case. So that's quite some challenge there. So now let's come back to the architecture. So what are these IoT devices in this case? So the IoT devices are the vehicles itself. So one of the main IoT devices is a vehicle. So if you look at the vehicle, they have an in-vehicle platform and provides quite a lot of services. So the most important ones, for example, when we think of AVP, it's a parking maneuvering service. Another one could be the motion planning service. And for these services, for example, for the motion planning service, they need input. And it can be from, as Sven already mentioned, it can be from their sensors, but also if we have the internet, we can extend their range by, for example, having the information from a remote parking spot, whether it is occupied or not. So such kind of input is needed for this motion planning service. And then, so this has an IoT gateway which interacts with the IoT platform to get this data. And then another service is the app itself. So the app can be used to start and stop the application or send commands to the vehicle to retrieve back the vehicle from the parking lot or send it to the parking lot. And so there is also a communication between the app and the IoT vehicle. And in the background, there are services running, for example, the valet parking service. So it has a user management service, parking management service, and also can support with the route selection service. I also mentioned that with the IoT, we can connect other sensors. In our case, the other sensors are the infrastructural cameras. So these cameras on the buildings or in the parking lot, stream live data, and then from there, some intelligent algorithms will process this data and then send out the information like the parking spot is occupied or the parking spot number X is free. And in addition to that, we also have drones in the use case. So the drones can also provide maybe some places where the cameras cannot cover. The drones can easily fly and see the status and also update that, okay, whether the parking spot is free or the obstacle, if there is any obstacle to that access roads to the parking lot. And so all these data coming are now stored in the IoT platform in different containers. And now when we look at more close with the data flow, we can see that, so the first, this is just an example how we have implemented it in the one of the test fests we had a few weeks back. So the infrastructural cameras sense their raw camera data information, and then our partner Vcomtech, they have an intelligent algorithm which is processing these camera images and then sends out the information like the parking spot status or obstacles. It's using and these algorithms are actually located in the server, and from there we use a messaging protocol called asynchronous messaging queuing protocol, so to send it to a task parking spot entity. And from these task parking spot entity, it is sent to the IoT platform. But as I mentioned, the TNO task vehicle can directly subscribe to this message and then get it from the 1M2M platform. But the DLR vehicle is using a different platform, that's the IBM Watson platform. And to make it interoperable, it's a bit more complex than this simple picture, but there is an interworking gateway or proxy which is translating this message from the 1M2M platform to the IBM Watson platform. And so then the data will be available at the IBM Watson platform. IBM is using a different messaging protocol called MQTT for their communication, whereas in the 1M2M it supports MQTT or the RESTful API, that's the HTTP, post, get, push for communication. Now, the task can also send this information directly to the IBM Watson platform for evaluation purpose. So this is basically the data communication flow. And in the case of drone is also sending this information directly to the IBM Watson platform. So in summary, this IoT enables data sharing between multiple parties. And also in our use case, one of the complex challenge was to use two different IoT platform, and we have also demonstrated that their interworking can be made successful, and this data sharing between these two platforms are also working fine. And in our case, we have also used standardized data models adapted from the DATEX2 model, and then that is used for sending out this parking spot status or obstacles. And in the next one slide, just show how this data is stored in the different containers in the 1M2M platform. So you can see that this AE task is like a big container, and inside that we can put a new container called AVP, and there another container called parking spot entity, and where the parking spot status. In this parking spot status, all these content instance about the updates of the parking spots are coming. And if you look at the right side of the picture, you can see the message, but this is not the standard JSON format adapted from the DATEX2 model, but this is one of the preliminary versions we used in the project. So if you look at the JSON message, you can see like the parking spot 0, 1, and 2 are available, whereas the 3, 4, and 5 are occupied. So this is the basic structure, how we store this data and then make it available to the different parties. Now, Jorge from Vicomtech will continue with the video surveillance part.
Yeah, hello, good afternoon. I'm Jorge Garcia, and I'm going to present the video surveillance sections. So regarding to the current scenario in video surveillance, it's totally different with respect to, for example, to the last 10 or 15 years. So now we can take advantage of the video data, not just to be used with safety or security application, but there are several new applications that we can use that kind of video data. One of them is, for example, the detection of free parking spot, that to know if there is availability to park a vehicle in a parking lot. So the goal of this application is to recognize available parking spot using video surveillance cameras that is currently installed in an environment. So this technology is based on deep learning model. For example, the network that we are using now is a convolutional neural network together with a classification step. So the convolutional neural network is responsible to extract the discrimination features and use it to to differentiate between a spot with vehicles and empty spots. So the novel in this work is the future extraction techniques. These techniques are more powerful than feature designed by humans. So after we have a convolutional neural network, we use a fully connected neural network to learn the discrimination between the two levels. In that case, we are using spot variables and not available spot. So particularly this deep learning model had been trained using around 500,000 images in order to have a lot of power to detect the parking status regarding to several weather conditions. So when we have a deep learning model which is able to differentiate between available or not available parking spot, we have developed for the current use case in AUTOPILOT a real-time application that is able to send the parking spot status to the IoT. We send this information through the task services, and then the task services are able to publish that information in the IoT, and this information can be used by the autonomous vehicles to use that information. So regarding to some specific features of the IPP of the application, for example, the application can be configured to check the parking status every certain time period. So this is totally configured, and also there is the application includes other features like to be careful when motion or other situation can happen in the parking spot. So in that case, we prefer to not update the status of the parking spot and wait to change the status of the parking spot just when the parking the motion or the image of the parking status is not changing. So currently the major problems that we have with this kind of application is possible occlusion with the perspective of the camera. If a particular parking spot is occluded by some obstacle or even other cars, the application is not able to know the status. So the preference to have a overview views of the environment. And now I would like to show you a sample of the application. This is the first status of the parking spot application, and we can see that when the application starts, we have defined some parking spot, and the status is recognized by the application. In this case, these four parking spots are occupied, and these two parking spots are free. So if we go ahead to see, for example, a change in the parking spot, now we can see that a person is going to the vehicle, and we can see if the car leaves the parking spot, the status of the parking spot will change. Now the car leaves the parking spot, and the parking spot will be available in a period of time. So now we have available, and this current status of this parking spot will be sent to the AOT to notify that the parking spot is free. And as I said before, if we have some motion in the environment, for example, now a car is, let me, there is a car, but I can see now. Oh, sorry. It's just to show that the motion in the image don't affect to the parking spots. Let me. Yeah, sorry. Sorry, but I cannot find where is the car moving in the video. Sorry. Well, okay, doesn't matter. In conclusion, is that the parking spot application is able to send the status of the parking spot to the IoT, and this information will be useful for the autonomous vehicle to use this information to park the vehicle. So now I'm gonna leave the tour to Robert to explain the next section about the drone.
I hope you can see now my presentation about the drone application.
Yes,
in full screen. So basically, in addition to the video camera surveillance just presented, we use a drone as IoT device in the AVP use case. So basically, the drone itself does actually the same as the roadside unit cameras. The drone as itself is a set of two things. It's a micro air vehicle, or MAV, and a ground station, which is basically a PC. And this entire system acts as an IoT device in the AVP use case. So basically, the MAV is able to navigate autonomously in the outdoor, but also indoor when we have no GPS signal available. The MAV sends the information about the parking area, flying and hovering above the parking area, detecting empty parking spaces and occupied parking spaces. This information are detected by the cameras mounted to the MAV, and only the information that parking area is free or not is sent to the IoT platform. On the next slide, you can see some basic information about the drone. It's basically a very light version of a drone. The weight is 2.6 kilograms, and the flying duration is approximately about 10 minutes. And it has two stereo cameras with a field of view from top to down of 240 degrees and from left to right with 80 degrees. So basically, I will show you on the next step a video how the drone works in the entire use case. Here we did first tests. So basically the idea is that an autonomous vehicle arrives at a drop-off position. The driver gets out of the vehicle and uses his smartphone. Via the smartphone, the drone will be started, so a request is sent to the IoT platform so that the drone starts and hovers above the parking area and detects the empty parking spot between the two vehicles. Then the car driver can confirm this parking slot, and the car drives in this empty parking area. And after that, the drone will fly back to its original base station and will land. And here you see the parking of the vehicle. And the same happens then vice versa when the driver picks up his car from a pickup area. So on the next slide, Sven will present the outlook.
Okay, thank you, Robert. Could you make me presenter again?
Yes.
Okay. So let's move ahead to where we. Yeah. So this finally I. Give an outlook to the automated driving and piloting. What you can see here is a facility we have in Helmond, indoor. We use these facilities for different applications, but now we have made a setup for developing automated valet parking. And the main research topic is the maneuvering and positioning of the vehicle. And well, we have to assume that not always a GPS connection will be available, and even when it is available, it may not have sufficient accuracy. So in this, to overcome this, we developed the vehicle to operate with LiDAR-based sensing using in the SLAM configuration, meaning that the LiDARs are used to create an image of the environment, a map, and at the same time it will provide the position of the vehicle within that map. So that means simultaneous localization and mapping. And of course, these LiDARs can also be used for obstacle detection, which you can see in this animation. The other thing you can observe in this animation is that the maneuvering for parking it's a high maneuverability that you need in order to park the car at the right location. So this is concerning the positioning, which is still a main challenge to make it work. There's quite a lot described in literature, but to make it operational in real time is not an easy thing. And the other part that we already developed is allowing driving for parking maneuvers in full automated mode. Here you can see the inside of the car. It's automated steering and automated speed. The driver is in there, well, not only for safety reasons, but also to select the gear from forward driving to rearward driving. And of course, in general, for automated driving, we will start with forward driving. That's the most what you do. But of course, for parking, we need to consider also backward driving. So this development is still going on, and it is a big challenge to really make that work. Okay, but then to move forward, the autopilot, it's in the name, is about piloting automated driving and Internet of Things. And what you see on this screen is the status we have concerning the pilot execution in the Brainport. So until now we have organized 2 events for integration of the technologies of the different parties involved. We have to consider that in the Brainport, the very large shared consortium is active in supporting the different use cases we have. We have about 15 partners involved and also a handful of associate partners. So it's quite an organization, and yeah, not all the parties are from the Netherlands, so we really need to organize an event to have everybody available at the same time. And we have done that in January and again just a few weeks ago. There we also made the step towards pilot readiness verification and validation about functionality for piloting. So in the piloting itself, we are considering at least 2 system variants. In 2019, the main focus is on the service concepts and the automated driving for the use cases, individual use cases. Whereas for 2019, we're looking at the integration of the different services. So, for instance, you can combine car sharing with automated valet parking and platooning, because you share a lot of the information and the logistics of the vehicle. But secondly, we also will be extending the automated driving for 2019. And finally, we will have public demonstrations in conjunction with the ITS 2019 conference in Helmond Eindhoven area. So if you look here in the timeline, we are now at the midterm of the project. We switch over from development and go into the piloting and evaluation. The objective of piloting is to be able to evaluate the impact of IoT on automated driving. And here you can see the events that we planned. So we have first piloting just after the summer in September, mainly on a technical evaluation of the different use cases and services. And in December 2018, we have an event with a local workshop where we also have external audience and also look at other aspects for evaluation. As said, we will extend the functionality towards 2019. So we plan another piloting event in March, and the final piloting event in May. This is just a week before the ITS conference. It's also preparation for the demonstrations which will be conducted at the 2019 ITS conference in Helmond Eindhoven. And then finally, the end of 2019 will also be the end of the AUTOPILOT project. So I would like to thank you for your attention. And of course, we are open for questions. In the meantime, you can look at this animation. It's a simulation of the parking maneuvers, meaning that also the trajectory generation from one parking spot to the other parking spot is fully autonomous. The car is autonomous. It has the same maneuverability as the real test car that we are using. And yeah, this is really a demonstration of what we can do. So yeah, I open the floor for questions. So Cecilia, maybe you can take over on this part.
Hello. So we have actually at the moment only one question, and they are asking, based on your experience, what is the latency of data getting to the vehicle in your architecture? I'm not sure to whom is this the question addressed, but if any of the panelists can just answer it.
Yeah, I would say that maybe DLR, you have the most experience with this data exchange in your system. Could you give some indication of what kind of latencies we have to consider?
Up to my knowledge, it's approximately 500 milliseconds.
Yes, and I believe it's also related to the constitution of the IoT network.
Exactly.
Yeah. So, but Amy, could you explain a bit how that will work in IoT? I mean, if you don't find the answer in the first IoT service, I believe there's the methodology is also to expand the search to other networks. Could you explain a bit how that would work?
I mean, the question is like, what is the minimum latency you can achieve, or is it like, because depending upon the service, for example, if you want to have a parking spot status update, you don't need to update it every millisecond or every 100 milliseconds. So you can have latency up to a few seconds to update that one. But we have other applications. For example, if you have like really interested in some kind of obstacle information, and the platform currently supports like it can go up to 100 millisecond. 150 millisecond is a rough round time estimation. I have checked. That is when this cloud is hosted somewhere far apart. But we are also planning to change that one to an edge computing, where this can improve significantly, so the latency can come down to much lower numbers.
Yes, and in any case, we consider different levels of driving, as indicated in the beginning. We have the operational. This is the overview. So we have the strategic, tactical, and operational driving. So for the steer and speed control, we can only accept latencies in communication of, well, I would say 10 milliseconds, that order of magnitude. But when it comes to the decision making, so 500 milliseconds is half a second. That's still enough time to anticipate on situations on the road where you have to choose the different lane, or maybe adjust the speed that you are driving. So the latency definitely is also impacting where you can use IoT. The other aspect where you can use IoT is really the trustworthiness of the data. If it's, I mean, you cannot rely your choice fully on data unless you can trust the data. So it's not only about the latency, but also the trustworthiness and even the accuracy of the data that will define how you will use that in automated driving.
There is another question on regarding the video surveillance technology. The question, it said, it seems that your algorithm take more than 5 seconds to update the status of on an occupation. Are they just asking if it's that not too long?
Yes, let's explain. The time that we need to check one image is around 1 millisecond. So the convolutional neural network spend 1 millisecond to check around 10 entre 10 and 20 parking spots, depending on the size of the image. But we understand that the application, the frequency is not when the parking spot change, the velocity of the car to be occupied again is not so high, it's not so demanding. So we choose, for example, to check the parking status every 5 seconds. But I mean, depends of the application.
There is another question regarding the indoor autonomous parking. Does a pre-loaded indoor map is needed?
Well, no. At least it will depend on the type of system that you have. So we have noted that when we use our test vehicle with lidars, it takes just one round of driving and you have an initial impression of the map. But the methodology also relies on repeated detections to increase the confidence level and also the accuracy of the environment. However, this indoor is quite a simple and straightforward environment. When you go towards the real outdoor application, the environment is not so nice. So let's say if you go here to the, you can see we have very nice red and white marked barriers. The color doesn't matter for the lidar, but it's the dimension of this is really nice and straight. So that's very easy to determine your position. When you go to the real outdoor situation, you don't have these very nice straight markings for the lidars. So there the position is much more challenging, and so you do need to have a baseline map, but you also need to know which parking spots are open beforehand or which are not open, because otherwise let's say the system would get confused, because at some point there he's detecting obstacles which are not in the map. So there really is some kind of interaction or update sequence in understanding the baseline. The baseline layout of the parking will of course not change, but what needs to be preloaded is which spaces are occupied by cars, because otherwise you cannot do the localization.
There is another question. What are the positioning technologies that you have investigated?
I believe this is used for the drone. Robert, could you comment on that?
Yes, I can comment on that. Well, actually not yet. So the drone is basically flying based on two use cases or situations, as mentioned on the slides. It can fly outdoors, so it uses the GPS positioning, and when it flies indoors, it uses visual markers surrounding the base station, and then based on that, it can fly around, localizing itself in correspondence to the base station. But radio-based technology, we didn't implement it yet and did not test it yet.
Yes, I've seen that some of your colleagues brought some antennas, but I believe they did not use it. We are actually using ultra-wideband solution on the test vehicles in addition to the current radar systems, so that could also provide positioning information, and for the outdoor application we currently rely on RTK GPS. There's a base station from the GPS system itself, but there's also an RTK GPS service provided through 4G by TAS. Amy, do you have some details about that system that you provide?
I mean,
Amy, are you still in the call?
Yes.
I believe that the entry solution.
Yes, with the correction signals, I think we can go down to a few centimeters accuracy.
Yeah, so we do consider different positioning technologies, and for sure during the piloting we will use multiple technologies simultaneously in order to have redundancies. It's early times for automated driving, so we will not rely on a single methodology for positioning. Secondly, on the campus itself, the cameras, of course, you can use the cameras for detection of available parking spaces, but the cameras can also provide some indication or of where the vehicle is or where the vehicle itself is. Accuracy is not it's not very accurate, but anyway, it's another source of information that can provide the local position of the vehicle, and of course at parking maneuvers the speed of motion is very low. So it's also not too much time critical. In any case, for the parking itself, it is required to have last meter collision avoidance, which well, it's more or less standard technology on modern cars now, and they are already equipped with ultrasonic sensors and have self-parking capabilities when they are positioned close to a parking spot. So, but there are different positioning technologies considered, yes.
Next question, do you plan to demonstrate IoT AVP in real traffic situation, notably autonomous driving cars parking when other cars move into the parking lots?
Well, this is it is considered. In any case, when we do that, the other cars will always be operated by people involved in the project. So we will not conduct it in a real open public parking space. But it is planned also to look at situations where other cars may be driving around. But once again, there will not be any general public people. And for sure, there will not be allowed to be any pedestrians on the parking area.
Okay, the AD system you showed is implemented within the OEME car system, or it is an external one?
The system, the automated driving system, that well, there are different vehicles used for automated driving. So when we consider the test vehicle of TNO, I know most about that one. It's basically a standard vehicle where we change the controls of the vehicle, but apart from one extra camera, we did not even extend the sensing. We don't use the LiDAR for this automated driving function at this moment. So to a large extent, it's just an OEM vehicle where we change the commands to the steering and the drive system. Robert, so how is that done on your test vehicle?
Basically, it's very similar to yours, but in addition, we have an own developed in-vehicle architecture we are using in addition to the OEM architecture which is running on the vehicle. So it's a bit more than only the OEM vehicle we have running on the car. So this gives us a bit more of flexibility in bringing the AVP use case on the road.
Yeah, we experienced that the capability of the standard vehicle components is limiting actually what we can achieve with automated driving. Yeah, the alternative is to extend the vehicle systems with additional actuators, etc. But then it limits the use on public roads. So the advantage, or the situation we have is that we only have a software change on the vehicle for the controls, and we can deactivate that, which allows us also to use the same vehicles on public roads. And for certain functions that we have developed, we have road exemptions that also allows us to do experiments on public road.
We have just received another question regarding when NEV's cars will be available.
You mean, when you look at automated valet parking, it has been announced that it will be provided by the end of this year by one of the OEMs. But that's a system that mainly, as far as I could tell from the information I've seen, is relying on the infrastructure sensors to be added to the parking. So the car itself is more or less a standard car, but the sensing is then in the infrastructure. The methodology where we are really focusing on is to find a balance between sensing from the vehicle, sensing from the environment, but then sensor types that could be exploited through the IoT system. Really also looking at what, like the camera system we are now using for valet parking application. It's just a simple surveillance system. So look at early deployment, low cost options as well.
Okay, I think that's all the questions we have.
Okay, well, if this was the last question, then it seems that we we are stopping at 5 o'clock with the presentation. Cecilia, could you maybe do the final slide that we see here?
Yes, so we would like to thank all the participants for being here attending this webinar, and we invite all of you to stay in touch with us through the website, so www.autopilot/project.eu, or follow us on the social media. We are on Twitter and LinkedIn. Also to subscribe to our newsletter, where we're gonna be sending news related to automated driving and information about our pilot sites. This recording will be also will be available on the website, so we will be inviting you to keep in touch with us and connected, and you will have all the information is interesting. Thanks to everyone. I think that's
okay. Well, anyways, thank you for hosting, giving us the opportunity to make this presentation. Thank you.
Thanks. Goodbye.